When people hear the words quantum mechanics, they often lose interest right away. They think of quantum mechanics as something to do with electrons and neutrons. It's not something that affects their day-to-day life. However, this isn't true at all. Let's take the example of the tools we use almost every day, our laptops. They wouldn't even exist without our understanding of particles, and to understand that, we need to go back to the beginning of quantum mechanics. Originally, the Greeks thought of atoms as the smallest unit of matter. They thought that if you kept cutting an object into smaller and smaller pieces, eventually you would reach a stage where it could not be divided any further. This was called the atom. To create a visual understanding of the processes in the atom, we construct models. The priority of these models is not their truthfulness, but rather their usefulness. For example, the Bohr's model, which shows electrons orbiting the nucleus like a solar system, is one that comes to many minds when thinking of an atom. Although it has been updated to the more accurate electron cloud model, the Bohr's model is still taught and used for understanding the emission of light. Models of light are generally separated into two categories. Firstly, the wave model, which shows light as a wave with a wavelength, wave speed, amplitude, etc. Secondly, we have the particle model, which shows light as a stream of tiny particles. Einstein thought of particles of light as electromagnetic energy made into concentrated packages or bundles. He was building onto the ideas of Max Planck, who said that atoms don't continuously emit and absorb light like a wave, but do so in little bundles called quanta. Essentially, a quantum is the unit for the smallest amount of something. For example, if we take the mass of this gold ring, the quantum is the mass of a single gold atom. The quantum always has to be a whole number divisible of the total. In this case, I could multiply the mass of the single gold atom by a certain number and get the mass of the whole ring. Einstein went one step further to say that light itself is built of quanta. The quantum of light, or any electromagnetic radiation for that matter, is now called a photon. Einstein's quantum theory of light was supported by the photoelectric effect. Basically, metals that are sensitive to light, or photosensitive, will eject electrons when light falls upon them. The brightness of the light beam corresponds to the number of photons. The energy of the light beam corresponds to the frequency. That is why a bright red light cannot displace any electrons from a metal, whereas a dim blue light can. We know that different colors have different frequencies, but Einstein explained this further using his knowledge of photons. Essentially, when the atom in the metal absorbs the light photon, it is an all or nothing process. It is either successful or it's not. Also, each electron that is ejected from the metal absorbs one and only one photon. Therefore, it doesn't matter if millions of red photons are shined upon the metal. If their frequency is lower and their energy is insufficient, they will not be able to eject even a single electron. However, even if there are only a few photons of blue light, each can still eject one electron because of its higher frequency and energy. Now Einstein used this information and realized that if light was a wave, it would be spread out and broad. It is unlikely, or rather impossible, that the energy could be focused on a single electron. To put this into perspective, it would be like a wave crashing on a beach and all the energy just focusing on one of the boulders. This is very unlikely, and it is more expectable that it would spread out amongst all the boulders. In the same way, if light was a wave, it wouldn't focus on one electron, but rather hit more of them. Using this information, it can be concluded that when traveling, light is a wave. However, when it has to interact with matter in a more concentrated manner, it is a stream of particles called photons. The American physicist Robert Millikan checked Einstein's work 11 years later, and each part of the interpretation was confirmed experimentally. Einstein received his Nobel Prize in Physics for his work on light. Louis de Broglie, a French physicist, started to question that since waves could have particle properties, couldn't particle also have wave-like properties? We know that an electron stays in different orbits around a nucleus. In each such orbit, it has a different energy. It can be said that it is on a different energy level, and scientists were able to identify these levels by observing how the electrons emitted light. However, they were still unsure about why these energy levels were at separate and distinct distances from the nucleus. This was solved when de Broglie proposed that electrons can be thought of as waves rather than particles. He believed that as the electron moves around the nucleus, it resembles a wave, and since the orbit is circular, the electron wave will come back around and reinforce itself. In this view, the electron cannot be visualized as a dot located at some random point in the atom. It can instead be visualized as if its mass and energy have been spread out into a standing wave that surrounds the nucleus. This wave must close in on itself in phase. This means that the crest meets the crest and the trough meets the trough. This will allow the electron to reinforce itself and keep going. If the electron wave meets out of phase, destructive interference may occur and the wave could cancel itself out. This theory solved the earlier confusion. Since the circumference of the electron orbits have to be discrete to allow them to complete in phase, the distance of the electrons from the nucleus is also discrete. Many inventions such as the electron microscope and the laser were made possible because of our knowledge of light and electrons and how they can be manipulated. The invention of the transistor, a tool used to control electric power, was also made possible because of quantum mechanics, and this invention led to the rise of laptops, a tool you're probably using to watch this video right now. Quantum mechanics has already led to a higher interest in a possible technology for the future, called a quantum computer. This may be able to perform at thousands of times the speed and hold much more data than a traditional computer. It can now be seen how quantum mechanics exists all around us and can improve our lives in many ways, and who knows what the future may hold.